For today, we will proceed with the unit on geologic time. Take notes. At times I will ask you questions and give you a few seconds to write down an answer. These questions are designed to help you learn about the topic in today's activity. After you complete watching the video, print and fill out a hard copy of this week's activity. This is due in class the following week. We will briefly discuss this assignment in class. This diagram shows the history of the Earth. Beginning with the Big Bang, the universe began about 13.7 billion years ago. Much later, the origin of our very own solar system was about 4.7 billion years ago. I like the spiral version of this time scale because it shows the geologic time, the geologic eras, the geologic periods, and the geologic epochs as they relate to the evolution of life on Earth. The geologic time scale is largely based upon this evolution of species, a product of natural selection, which also is sometimes controlled by geologic processes. There are two types of geologic time. Do you know what these are? That's right, relative time and absolute time. The image and drawing shows the rocks in the Grand Canyon. These are used to illustrate the concept of relative time. One of the basic concepts of relative time is the principle of superposition. This concept dictates that the youngest beds or rock units are superposed towards the top and the oldest rocks are at the base, if not disturbed. Fossils are helpful to determine which is older based on the evolution of life through time. In the drawing at the right, can you tell which is the youngest rock and which is the oldest? That's right. The red wall limestone at the top is the youngest rock, and the Precambrian metamorphic rocks at the bottom are the oldest rocks. Based on the principle of superposition, which rock is the oldest? 1, 2, or 3, or are they all the same age? That's right, rock 1 is the oldest. This painting at the right is from a story in Science Daily about an article in the scientific journal Analytical Chemistry. Absolute time is a measure of the actual number of years before present. The absolute time scale is based upon the radioactive decay of radioactive elements. These radioactive isotopes naturally decay from one isotope into another isotope. Elements are defined by the number of protons in their nucleus. Different isotopes are elements that have the same number of protons but a different number of neutrons. Radioactive isotopes decay from parent isotopes into daughter isotopes. Different kinds of isotopes decay at different rates, but each isotope of the same type has the same decay rate. For example, all carbon-14 decays at the same rate, and all potassium-40 decays at the same rate, but carbon-14 and potassium-40 decay at different rates compared to each other. The decay from parent into daughter isotopes proceeds with what we call a half-life. The half-life is the time required for 1/2 of the parent isotope to decay to the daughter isotope. For example, if we start with 100 parent isotope atoms and we wait until one half-life has passed, we'll have 50 parent isotopes left and 50 daughter isotopes. The table at the right lists the percentage of parent isotopes remaining after different numbers of half-lives. After 7 half-lives, there is very little of the parent isotope remaining. At this point, it may be difficult to measure this parent isotope. Therefore, isotopes with shorter half-lives are only useful for younger geologic materials. Where isotopes with longer half-lives are useful for geological processes and geological units that span much further into the past. This slide lists the half-life for 3 radioactive isotopes commonly used by geologists to determine the absolute time for some geologic processes. I love this graphical depiction of the 2 types of geologic time. On the left shows a depiction of relative time with rock layers containing the fossilized remains of past life forms. This was the first type of time that was identified. After we developed analytical methods to measure the quantities of radioactive isotopes, we developed the absolute time scale, represented by the column on the right. Note that the time scale is broken up into larger time periods called eras, the Paleozoic, Mesozoic, and Cenozoic, and smaller time periods called epochs. Note that the vertical scale on this time scale is non-linear. See how the Holocene epoch, which is about 10,000 years long, is the same vertical scale as the Paleocene epoch that is about 10 million years long. Each life form spanned a specific time period during which it evolved and changed form. Sometimes these species, called paleospecies, went extinct. Rocks that are deposited after these extinctions will not have any fossils from life forms that went extinct during these extinctions. There are 2 mass extinctions shown on the column on the left: the Permian-Triassic (PT) extinction and the Cretaceous-Tertiary (KT) extinction. The Tertiary period includes the Cenozoic era except for the Pleistocene and the Holocene. All dinosaurs went extinct prior to the KT extinction. Using the principle of superposition, would you expect to find dinosaurs in rocks that were formed during the Cenozoic era? You're correct. No, you would not. This is the Geological Society of America geologic timescale. I provide the link for you if you want to download it. We will be using this timescale periodically throughout the course. In Lab 1, we plotted the entire history of Earth onto some adding machine tape. Most of the time divisions were located in a very small portion of the paper tape. This graphic further shows how we could look at the vast history of Earth that is not well represented by the geologic timescale. What are the 2 kinds of geologic time? Yes, relative and absolute, or numerical. Based on your reading material, what is relative time based upon? Yes, relative time is based upon the principles of superposition, original horizontality, lateral continuity, and cross-cutting relations. It's based on inclusions, and it's based on unconformities, which include the angular unconformity, the disconformity, and the nonconformity. What does conformable mean? The continuous deposition of rocks. Based on your reading material, what is absolute time based upon? Yes, absolute time or numerical time is based on radioactive decay. What happened here? Yes, the rocks have been folded. Why do you think that? Based on the principle of original horizontality, these rocks were originally deposited horizontally. That they are now folded suggests that there was some form of deformation following their deposition. What happened here? Are these rocks the same rock units on each side of the river canyon? That's right. The rocks originally extended across the entire region. It is only because that the river eroded them that they are separated by the river canyon. This is an example of lateral continuity. Here we see some sedimentary rocks that have been cross-cut by an earthquake fault. Is the fault older than the rocks, or are the rocks older than the fault? That's right, the rocks are older than the fault since they needed to exist before the fault could offset them. This is an example of cross-cutting relations. Cross-cutting relations. What is a dike? A dike is an igneous rock intrusion. Magma flows vertically between other rocks, then later cools and hardens into rock. Is the black dike older than the white rocks? Or are the white rocks older than the black dike? That's right, the dike is younger than the rocks since the rocks had to exist before the magma could intrude into them. Principle of inclusions. If we find a rock fragment enclosed within another rock, we say the fragment is an inclusion. If the enclosing rock is an igneous rock, the inclusions are called xenoliths. In either case, the inclusion had to be present before they could be included in the younger rock. Therefore, the inclusions represent fragments of an older rock. In the example here, as the basalt flowed out on the surface, it picked up inclusions of the underlying sandstone. So we know that the sandstone is older than the basalt flow. Similarly, the overlying rhyolite flow contains inclusions of the basalt, so we know that the basalt is older than the rhyolite. This principle is often useful for distinguishing between a lava flow and a sill. Recall that a sill is intruded between existing layers, much like a dike, although a sill is horizontal and a dike is vertical. In this case shown here, we know that the basalt is a sill because it contains inclusions of both the underlying rhyolite and the overlying sandstone. This also tells us that the sill is younger than both the rhyolite and the sandstone. Here is an example from the textbook. As we saw in the previous examples, the intrusions existed prior to the formation of the geologic material in which they are intruded. What is an unconformity? Yes, an unconformity is a buried erosional or non-depositional surface separating two rock masses or strata of different ages, indicating the sediment deposition was not continuous. There are three main types of unconformities. An angular unconformity is where the tilted rocks are overlain by flat-lying rocks. A disconformity is where the sedimentary strata on either side of the unconformity are parallel to each other. A nonconformity is where sedimentary strata overlie metamorphic or igneous rock. The graphic at the right depicts the formation of an angular unconformity. Step 1, deposition of a geologic unit or units. Step 2, uplift and folding of this older geologic unit or units. Step 3, erosion of these older geologic units. Step 4, deposition of younger geologic units. Here's an example from the textbook. We can see that there's a lower geologic unit and an upper geologic unit that are separated by a lithologic contact. The lower unit is dipping vertically and the upper unit is dipping shallowly to the left. What type of unconformity is this? That's right, this is an example of an angular unconformity. Here, the lower geologic unit is dipping at an angle, the upper geologic unit is not. What type of unconformity is this? That's right, this is an example of an angular unconformity. Here, we see lower geologic units and upper geologic units that are deposited with their bedding parallel to each other. Between the upper and lower units is an unconformity that represents a period of non-deposition and erosion. What kind of unconformity is this? That's right, this is an example of a disconformity. This may be difficult to tell from this textbook photo, but here we have a lithologic contact between lower and upper geologic units that represents a period of non-deposition and erosion. Do the upper units and lower units have bedding that is parallel to each other? Yes, they do. What type of unconformity is this? That's right, this is an example of a disconformity. Here, we see that there is a contact between lower geologic units that are older igneous or metamorphic rocks and upper geologic units that are younger sedimentary layers. The unconformity represents a period of uplift and erosion when the once deep rocks were exposed at Earth's surface. What type of unconformity is this? That's right, this is a nonconformity. Here's another example from the textbook. This is from the Grand Canyon, where the lower and older Vishnu schist is separated by a lithologic contact from the upper, younger sedimentary geologic rocks. What kind of unconformity is this? That's right, this is a nonconformity. This is a figure from our textbook that shows all three types of unconformities are found in the Grand Canyon. We see a disconformity, an angular unconformity, and a nonconformity. Try to do a little internet research on this topic. Type in the following into your search tool: images of types of unconformities. Geologists seek to understand the geologic history of a region by looking at the time history of rocks located in that region. One important aspect of establishing a geologic history is to correlate geologic units across the region. This is done by matching the rocks in one area with the rocks in another area. This can be done by looking at the rock types, the fossils embedded within those rocks, the stratigraphic order of the rocks, and the numerical ages of the rocks. In this example from the textbook, there are 3 locations in the western USA that are distanced hundreds of kilometers from each other. The cross-section shows how the geologic units span this entire region. The stratigraphic columns in the lower half of the figure show how these sedimentary rocks all share a similar stratigraphic history. This shared stratigraphic history is the basis for correlating these geologic units from location to location. For example, for the Grand Canyon on the left, the Moenkopi Formation, which is colored gray, is on top of the Kaibab limestone, which is colored cream. This is also the case for these two geologic units in Zion. You can see dashed red lines connecting the stratigraphic columns between these three regions. A second example shows that the Carmel Formation, which is colored in gray, is on top of the Navajo Sandstone, which is colored yellow, in Zion, as it also is in Bryce Canyon. The stratigraphic sequence of these geologic units is an important aspect of stratigraphic correlation. Since we're talking about rocks, it is good to review the three main kinds of rocks. Do you know what they are? Yes, igneous, sedimentary, and metamorphic. We'll spend more time looking at these different kinds of rocks later. The figure shows the rock cycle and the different processes by which rocks can change from one type to another. You can find this figure in the textbook. Do you know what fossils are? That's right. Fossils are traces or remains of prehistoric life preserved in rock. Paleontology is the study of fossils. Knowing the nature of life that existed at a particular time helps researchers understand past environmental conditions. The geologic relative timescale is based on the evolution of life forms, and evidence of this evolution is preserved in the fossilized remains within geologic units. Some species, called paleospecies, are only found in the rocks that were deposited during the time that those species existed. These figures show macrofossils, fossils that one can see with their naked eye, and microfossils, fossils that require microscopes to identify. This figure from the textbook shows how life form species often have limited time ranges within which that they existed. Rocks that are older or younger than these time ranges will not include fossils from these species unless there was some type of geologic event that created an inclusion that contained these fossils. The graphic on the right shows the time ranges for some fossil groups. The fossil at the left is that of a trilobite. The fossil in the center is a dinosaur. Trilobites went extinct long before dinosaurs existed. Rocks with dinosaur fossils in them are younger than rocks with trilobite fossils in them. What if we find rocks with dinosaur fossils underneath rocks with trilobite fossils in them? There must have been a geologic event that placed older rocks above younger rocks. An earthquake fault or a landslide could do this. What are the principles we just reviewed? That's right. The principles we just reviewed are superposition, cross-cutting relations, original horizontality, lateral continuity, and three different types of unconformities: angular unconformity, disconformity, and nonconformity. Based on the principles we have just reviewed, we can interpret the geologic history of a region. You are now an expert in these relative age principles, so we'll now discuss absolute age principles. First, we must review the parts of an atom. This figure shows an atom and its main particles called subatomic particles. The three major subatomic particles are listed in the upper left-hand corner. The size of the symbol relates directly to the mass of the particle, though not entirely to scale. The legend also shows the charge of each particle. The drawing in the middle shows where these particles reside in the atom. Protons and neutrons exist within the nucleus of the atom. Electrons exist in orbits that encircle the nucleus. Based on your reading, do electrons have mass? Yes, they do. How much compared to protons and neutrons? The mass is about 1/2000th that of a proton or a neutron. The figure at the lower right-hand corner shows one way of displaying an element, or atom. There are three main parts of this configuration. X, the element symbol. A, the atomic mass number, which is the number of protons plus the number of neutrons. Z is the atomic number, or the number of protons. Elements are groups of the same type of atom. Atoms are defined by the number of protons in the nucleus. If an atom changes its number of electrons or neutrons, it becomes an ion or an isotope, but stays the same atom. If the number of protons changes, then the atom turns into a different atom. This figure shows that these orbits are actually clouds of electrons. However, different electrons do exist in different distances from the nucleus, depending upon the energy state of those electrons. These orbits are called shells. The outermost shell is called the valence shell. From your reading, what are the electrons that are in the outermost shell called? That's right, valence electrons. Atoms are individual objects that are referred to as elements. An element is formed by a group of a particular type of atom. The elements are organized into charts like the one shown here, called the periodic table of the elements. There are many examples of these periodic tables, so make sure you take a look at the legend to make sure you interpret them correctly. This one is from the textbook, figure 3.5. The legend shows that each element is labeled with the atomic number, the symbol of the element, the atomic weight or atomic mass, and the name of the element. What is the atomic number? What does that represent? That's right. The atomic number is the number of protons in a nucleus. Since elements and atoms are defined by the number of protons in their nuclei, this is how all of the periodic table of the elements are organized. What is an element? That's right, an element is a group of the same kind of atoms. Based on your reading, what is radioactive decay? That's right. When nuclei are unstable because the forces that bind protons and neutrons together are not strong enough, the nuclei break apart or decay, creating isotopes. Do you know what the isotopes are called prior to this decay? Yes, they are called parent isotopes. Parent isotopes decay into daughter isotopes. This decay, it occurs at some rate of decay per unit time. Do you know what this rate is called? Yes, parent isotopes give rise to daughter isotopes at a constant rate called a half-life. For every half-life, half of the parent isotopes have decayed. The figure on the left from your textbook shows the three kinds of radioactive decay. Alpha emission is a radioactive process in which a particle with 2 neutrons and 2 protons is ejected from the nucleus of a radioactive atom. Because the daughter isotope has a different number of protons, it becomes a different type of element or atom. Beta emission is a radioactive process in which a proton is converted to a neutron or vice versa. As a result of this transformation, an electron is emitted from the parent isotope. Because the daughter isotope has a different number of protons than the parent isotope, it becomes a different type of element or atom. And on the bottom panel, electron capture is a process in which a proton-rich nuclide absorbs an inner atomic electron, thereby changing a nuclear proton to a neutron and simultaneously causing the emission of an electron. While the number of protons changes and the daughter isotope becomes a different atom or element, because the proton turns into a neutron which has the same mass, the atomic mass does not change. This figure shows the 3 isotopes of carbon. The name of the isotope is under each illustration, along with the number of protons and neutrons and the atomic weight or mass. Can you tell what is different between these isotopes and what is the same? As a review, let's review what is an isotope. Isotopes are atoms with the same number of protons but different amounts of neutrons. So we can see that for the 3 isotopes, carbon-12, carbon-13, and carbon-14, they each have 6 protons but have different numbers of neutrons, 6, 7, and 8. And because of this, they have different atomic weights, 12, 13, and 14, which lead to the names of these different isotopes. Carbon-12, which has an atomic mass of 12, carbon-13, which has an atomic mass of 13, and carbon-14, which has an atomic mass of 14. This figure shows how carbon-14 is formed and how carbon-14 decays. The upper panel shows a neutron from outer space being captured by a nitrogen-14 atom. When this happens, the atom emits a proton and becomes the isotope carbon-14. The lower panel shows how carbon-14 decays to nitrogen-14 when a neutron converts into a proton and an electron is emitted. Note how the atomic number, based on the number of protons, changes and how the atomic mass, which are protons plus neutrons, stays the same. This figure shows how the count of parent isotopes and daughter isotopes changes with time. The initial time on the left begins with 16 parent isotopes. Each step to the right represents a single half-life when half of the parent isotopes decay into daughter isotopes. How many parent and how many daughter isotopes exist after one half-life? Yes, 8 parents and 8 daughters. How many parent and how many daughter isotopes exist after 2 half-lives? Yes, 4 parents and 12 daughters. How many parent and how many daughter isotopes exist after 3 half-lives? Yes, 2 parents and 14 daughters. All plots should have their axes labeled, and that is the first thing one should observe whenever they look at any plot. The vertical axis on this plot represents the number of atoms in percent. The horizontal axis represents the number of half-lives or elapsed time. The data that are plotted are the daughter atoms accumulated and the parent atoms remaining. In other words, this plot shows the number of parent and daughter isotopes that exist after a given number of half-lives. The vertical axis is actually incorrectly labeled. The label should not say percent, but since these data represent 100 initial parent isotopes, this mistake is not important. This table lists some radioactive isotopes used for determining the age of geologic units and processes. Which isotopes would be good to estimate the age of the Earth? That's right. Uranium, thorium, and rubidium all have long half-lives. Which isotope would not work for that? That's right, carbon-14. The half-life is so short that all of the carbon-14 that may have existed when the Earth was formed would have decayed by now. Let's determine the geologic history here. List the units and processes from oldest to youngest, and consider the basic principles we geologists use for relative time. The principle of superposition, cross-cutting relations, the principle of original horizontality, the three types of unconformities, and the principle of lateral continuity. Write down your interpretation for the geologic history based upon your knowledge of the basic principles as they apply to the drawing here. Pause the video until you complete this exercise. The video will have a 15-second break, but you probably will need more time than this. Sometimes it helps to start with what you think is the youngest and also what is the oldest. So list in order the oldest to the youngest and list which principle you use to determine that. All right. A is the oldest rock. Looks like the Vishnu schist to me. B is the next oldest rock. Superposition. C is the next oldest rock. Superposition. D is the next oldest rock. Superposition. And E is then the next oldest rock. Superposition. L. Dike L cuts rocks A through E. Cross-cutting relations. K. Pluton K cuts dike L. Cross-cutting relations. M. Dike M cuts Pluton K. Cross-cutting relations. F is the next oldest rock. Superposition. G is the next oldest rock. Superposition. H is the next oldest rock. Superposition. J is a fault that cuts older rocks. Cross-cutting relations. And I is a rock that's not cut by the fault. Cross-cutting relations. Here's a bonus illustration. On your own time, take a look at this illustration and try to determine what the order of events that led to this configuration of geologic units. Pause the video if you want to do this now.